So Andreas Rossberg will present our keynote talk, Is Wasm Becoming Garbage? Andreas did his PhD work at Saarland, I believe, and postdoc at the Max Planck Institute for Software Systems. After that, he was employed as software engineer by Google, working with the V8 team. They produce the JavaScript/Wasm virtual machine engine. And since then, he's been an independent implementer, researcher, etc.
Not quite.
Not quite? Okay, well, I'll let you introduce more. So without further ado, we welcome Andreas.
For the nice introduction and for having me. So yeah, the only thing that wasn't quite right, there was another, like I was at a startup in between before, like after Google, but that's okay. Okay, let's see how this works. Okay, yeah, again, thanks for having me. I'm talking about WebAssembly, as Elliot already said, and especially about the new feature we have there, one of the new features we have there, which I'm excited about, which is garbage collection, which is the fit for this conference, right? So WebAssembly, I don't know, who in the room is actually familiar to some degree with WebAssembly? So, okay, most people have seen it, I guess. Nevertheless, let me start with getting out of the way one or two misconceptions about WebAssembly. The first one being, it's a web technology. It's actually not a web technology. And I mean, it's easy to take it as that, given the name and its history, but we actually made very sure when we designed it, so WebAssembly grew out of the frustration of various JavaScript implementers with like wasting their life on this kind of thing. They wanted to do something more meaningful. So it's more like a historical accident that we called it WebAssembly. That, from my perspective, that was a way to convince management to adopt it, because to management at the time, the web was the only thing that mattered, right? So that's why we christened it that way, one of the reasons anyway. But really, the whole design was, from the get-go on, intended to be much more than just the web, really like not specific to the web at all. And we anticipated that it will be used in all sorts of contexts, and we are amazed to see that that actually happens. So it's now running in basically every kind of ecosystem you can think of, including things like embedded, and which is like the opposite end of the spectrum. And that is why I personally prefer to not emphasize the web aspect too much and just call it Wasm, which is the short form, which, by the way, you spell this way, not in all caps, because it's not an acronym, so no reason to shout it. But with that out of the way, let me actually explain what it is. So WebAssembly, maybe the best way to think about it, it's a virtual machine. But it's a low-level virtual machine, like unlike other mainstream VMs you're probably familiar with as well. It's also designed to be language independent, right? So there's no language that has any particular privilege on this platform. It's also platform independent, meaning that it's designed to be embeddable anywhere, right? So the browser is just one example, but really it's you can embed it anywhere, and there are actually dozens of different implementations of WebAssembly, a dozen different implementations now, I lost count to be honest, which kind of are designed for different spaces, like very tiny ones for embedded, for example, and so on. Part of the design is that it's the language, it's kind of a language, obviously, so it's designed to be very portable, deterministic, up to some minor quibbles, and sandboxing is also an important factor in its design. And finally, the specification is an open standard. So, what happened? Wait, see. Meaning that it's happening under the roof of the W3C, but everything, the entire process is totally in the open. All the discussions about proposals and stuff are on GitHub. We have bi-weekly meetings on Zoom where everybody can participate, essentially. It's completely open. Everybody can vote as well. And yeah, and there are various other subgroup meetings. You could just show up if you wanted to. All you have to do is register with your email, I think, for legal reasons or something. Right, okay, so and the first item I say there is low level, and I want to stress on that a little bit because that's maybe relevant to my talk. So what do I mean by low level here? Well, there are various ways you can various characteristics you can use to describe this, but the slogan I'm using, or the general idea perhaps, is this one, right? So unlike other mainstream VMs, Wasm really is an abstraction of the hardware below. It's not an abstraction of some programming language. So for example, compare that with the JVM, which is really more or less in the first approximation abstract syntax for Java, right? And .NET is similar. Wasm is not that, and which means that really all the languages you could possibly implement on it are equal citizens. There's no language that has any particular privilege here. And as far as I'm concerned, if you want to have a language-neutral VM, that's the only way to do it. It has to be a low-level VM. Everything else will inevitably get you into some rabbit hole with language-specific features, which we try to avoid. So more concretely, it's essentially an ISA, a virtual ISA, so an instruction set that is inspired by what actual CPUs offer. So it's really in the intersection of what modern CPUs have, at least like the initial design. So and almost every instruction has a one-to-one mapping to popular CPUs. Another part of it is that the cost model we have for WebAssembly is supposed to be very transparent and explicit, right? So with every instruction, you should be able to tell how it's compiled down by the engine to native code and what it does. So there are supposedly no hidden branches, no hidden allocations or things like that. If you have to do any of these, that should be explicit in the code, at least in the first approximation. And the goal there is that performance is really predictable, right? So you know what you're going to get. Another part of it is that there's no such thing as an object model, right? That just doesn't exist. You have memory, at least for now, and you do with it what you want. In particular, WebAssembly is designed to not require GC. And finally, another aspect of this low-level nature is that we assume that most interesting optimizations are actually done by the producer of WebAssembly, so a compiler targeting it, not by a consumer, which is the engine. So the engine can be relatively dumb. They just translate the Wasm code to the native code they're running on, and they could be simple and fast. And in particular, they could work ahead of time. So we also don't want like any super fancy dynamic mechanisms in there idly. So that's the ideal as anyway. Of course, in practice, it doesn't quite work out like that. So you may ask the question, how low can we actually go, right? And the reality of things is that we are working in this triangle of conflicting goals, design goals, that we have to maneuver somehow. And actually, it's not just a triangle, it's a tetraeder, because one of the constraints we absolutely cannot compromise on is safety, right? It absolutely has to be safe. So we need to balance these constraints, and sometimes balancing these constraints means that we have to raise the abstraction level somehow. So the slogan I've been using, and which also was the title of another recent talk of mine, is that, yeah, it should be as low as possible, right, but no lower. And to give you a concrete example of how this already materialized in the initial design of WebAssembly 1.0 is consider like functions, how functions work in WebAssembly. So in WebAssembly, all code is organized into functions, right? They are a primitive notion. You declare their parameters, you have dedicated instructions for invoking them and so on. And that obviously is something that does not exist on CPUs, right? They don't have that. You just have code and you jump around. But that's not what we did, and there are several reasons to it. One is safety. So we don't want to expose the stack, right? Because they're like, it's a very beloved attack vector, among other things. And also we need to be type safe and things, which is difficult if you expose the stack in a primitive way. Another reason is that the producer, so the compiler that generates WebAssembly, doesn't know what actual physical hardware it's running on. So it's difficult for it to optimize like its code gen, like in terms of register allocation and things like that, parameter passing conventions and so on. But the engine knows what it's running on, so the engine can do a much better job of that, right? So this is like motivation for raising the abstraction level a little bit. We also don't expose code pointers, physical code addresses. Instead, we have this notion of tables. I don't want to dwell too much on that, but again, this has to do with safety and not wanting to expose certain low-level things that might be problematic. But even though we're raising the abstraction level a little bit here, it's still the case that functions are just code, right? If you have a reference to a function, it's really a code pointer, and we don't have anything like closures in there or, God forbid, methods, anything like that, right? That's not in the language. That's something you have to implement on top. Okay, and why am I telling you all this? Well, if you now hear I'm talking about garbage collection WebAssembly, that seems to kind of like run against everything I just said, right? So how does that fit in there? And before I explain that a little bit, let me just briefly say what the current state of this proposal is. It's actually done. So last month we voted it into the standard. After 6-7 years it was in the making. It probably was the most complicated proposal we had so far. And it's already targeted by various compilers. So for example, a Java compiler, Dart, Kotlin, there's work in progress on OCaml and Scheme, and probably many others I'm not even aware of. And this is not just work in progress, or at least not all of it. It's actually already used in production. So for example, the Java compiler is used by the Google Sheets team. Google Sheets is written in Java, and it used to compile to JavaScript. Now they are ramping up the transition to WebAssembly, which means if you run the latest Chrome and open Google Sheets, there's like a 1% chance it's already running the GC proposal right now. Okay, but again, garbage collection in WebAssembly. The question you should be asking is why? Why do we need that? Or why do we want that? And WebAssembly has this notion of linear memory, so just a linear address space, that's all yours, you can do with it what you want, so can't you just roll your own GC in that, right? And yes, you can, and various languages have done that, and various languages will continue to do that. It's not a bad thing to do, and there are all sorts of reasons why you may want to do that, but there's a cost to it. And the cost has to do with the abstraction levels that we have in WebAssembly. So for example, you don't have access to the stack, as I said, you don't have access to registers, so this makes things like traversing, like walking the stack in the GC a bit difficult. You have to do workarounds like shadow stacks and stuff, which make it more costly. You also have the issue that production GC is really like, it's quite big, right? So if you, say on the web, want to ship a GC with every web page, that's kind of annoying. So if I remember correctly, so there's a mono port to WebAssembly that has existed for quite some time, and if I remember correctly, the runtime is pretty big, and it's just the GC alone is like 0.5 megabyte of code or something like that, or even more than that. Another issue is that, again, take the web as an example, you may want to access the host environment. So on the web, that would be JavaScript and the DOM, and be able to have reference to DOM objects, for example, and pass them around your your WebAssembly code. And if there is like no coordination between the two worlds, then that is very difficult to do. And that's what currently languages do, but it's really hard to have a safe memory management story there. And then you have the general problem, of course, that if you have multiple runtimes running, say, in a web page, then you have this common problem of competing heaps, competing GCs, and that's, again, like a performance problem. And, of course, finally, at least on the web, we already have these industrial strength GCs right at our fingertips, right? They are there. There are like dozens or even hundreds of man years went into the engineering of these things. They're probably the most advanced GCs out there. So it would be sad if we could not take advantage of that. So all these are reasons. There are some more. There are also a couple of non-reasons I should mention, non-goals of this proposal. And one is that we somehow magically achieve language interoperability between different languages compiling to WebAssembly. That in general has never been a goal for WebAssembly, and very intentionally so, because it never works, right? So this is like a separable problem from our perspective. So if you need interoperability between multiple compilers compiling to WebAssembly, well, you can do that. You have to define an ABI, the same thing you do in native code, right? You have to agree upon what your compilation scheme is and stick to that. But that is something you can define on top of WebAssembly. It doesn't have to be built in. And that carries over to GC as well. And as far as I'm concerned, this is key to Wasm's success as a language-neutral technology. Okay, so what we instead want to do is really we want to provide GC, but stripped down to the bare basics. So no complex type system. It should be the types in it should be very simple to produce and to consume. And the basic idea is we just describe memory layout. We just tell the GC how we want to lay out our data in memory and let the GC figure out how to manage it. It's not like something that is directly related to source level types like objects or something. So that means if you have a high-level language with some Rube Goldberg type system, you must lower it to WebAssembly, like you lower code as well. You have to lower your types as well, right, to whatever simple thing WebAssembly actually provides. And the key takeaway here really is you have to do it more or less the same way you do in native code. That's what I mean by garbage collection actually being low-level as well in our proposal. And another part of it is that the whole design of this extension is supposed to be pay-as-you-go. So again, there should not be any hidden costs. All allocations are explicit. And also, if you don't use any of the GC-related instructions or features, you should not pay anything. And as part of that, we wanted to avoid all sorts of old problems, like language-specific constructs, heavyweight object systems or types. Things like reified generics are certainly not something we want to adopt. Sorry, Andrew. Or unsound type systems, like arguably in Java, where you can have method or attribute access failures at runtime. And also we want a modular semantics, so WebAssembly has a module system, a very strong one, which full encapsulation, and you want to be able to lower, like when you do separate compilation in the source language, you want to lower the modular structure to WebAssembly. And which means that things like nominal typing, for example, on the low level would be problematic because if your source language is structurally typed, then there's no way to maintain your modular structure if you have to lower it to a nominal system. Okay, so what is it that we have? We really stick to a couple of very simple primitives. First one just being tuples. It's one thing you can allocate, and they're like this heterogeneous thing that you can statically index, and then kind of the opposite are arrays, which are homogeneous, but in exchange you get the ability to dynamically index into them. And this distinction all has to do with typing, right? So I'm gonna get back to types in a minute. And then the third thing we have is scalars. So most managed languages actually use some kind of tag pointers so that they can unbox integers, and we want to make that available as well, right, as part of our low-level story. So that is another feature we directly provide. You can use unboxed integers in the pointer space. And the last bit is just functions, which are essentially just code pointers. So again, no closures, just code pointers. And just briefly mentioning, there's one fifth thing there, which is like external pointers. So you can embed pointers to host objects as well, if you need to, but I'm not going to talk about that here. So these are our primitives. That's all the GC proposal provides. And everything else has to build by you on top of that, right? So the GC knows how to manage these things, but that's all it knows. So more concretely, in terms of WebAssembly syntax, we have these new forms of type definitions for structs and arrays now, and on the right-hand side you have new forms of value types, is what they're called. So these are the types of locals or parameters or something, where previously you only had like I32, F64 and stuff. You now have these reference types, which are referenced to a specific type, and there's a flag on them as well that tells whether this can be a null or not. So we distinguish nullable and non-nullable for performance. And yeah, the third thing is this scalar kind of thing that's modeled as a reference to an I31. Why I31? Well, we have to be portable, and we want to have predictable performance. So the largest type we can guarantee across all relevant platforms to be actually unboxed is like a word size of 32-bit. We need 1 tag bit, so that's how you get to 31, right? May seem a bit odd at first, but that's the situation we have to maneuver. Yeah, and so these are the types, and then you have the kind of canonical instructions for dealing with them, so for allocating stuff and for accessing them. And there are a bunch more instructions, but really this is the core set, and the others are more like convenience. A couple of side notes here. So first of all, the allocation of these things happens on the GC heap, which is completely disjoint from the Wasm linear memory. There's no interaction whatsoever. And this heap also is not exposed to programs at all, right? You get these references, but that's all you have. And these references are completely opaque as well, so you cannot observe what address is underlying them as a representation. So programs cannot observe that, and again, the reason is safety, right? We don't want native pointers to leak into the program space. So you can't store them in memory either, because that would like break this abstraction, violate this abstractions. But instead, we repurposed this notion of tables that already existed in WebAssembly for functions and indirect functions, and generalized them to arbitrary reference types. So that is your storage for references. You can now define tables, multiple tables, and store references in them. And that gives you a numeric index, which you could store in memory, for example. Okay, so type system, I kind of glossed over that so far, references are strongly typed, right? And the motivation here is that we want to avoid any overhead whatsoever in accessing heap allocated objects. So there should be no runtime check, no matter what you do. Like, again, unlike the JVM, for example, where semantically there is a runtime check for every access. VMs often can do dynamic optimizations and stuff to get around that, but that's not what we want to have in WebAssembly. So for example, if I have like a type declaration for a point, like a tuple of 3 fields, and I could implement like a little function that just accesses the first thing there, the first component, and this struct get is just a simple load, right? That's all it does. It's a load, indirect load through a pointer, and it can never fail. There's no check involved whatsoever. And you also know that what you get back is actually an F64. So this is all validated by the type system. And this typing is deep, right? So it's not just we know that this has fields of F64. You could, for example, say I define an array type of reference over points, then you know like all the way down what you get. Like when you do multiple indirections, you already know what you get. So all this typing is deep, like you really expect from a proper programming language. Yeah?
So prior to GC, to generate this kind of code, you wouldn't have struct, so you've done your own indexing and so on and so on?
Prior to GC, yeah, you would have to lay out all this in memory, essentially. Yeah, that's...
It's a completely different way.
Yeah, and this is a completely different way of doing that, so... There's also subtyping, because often you want to compile a language, source language that has subtyping, and ideally, whenever you use subsumption in the source language, you don't want to have like a conversion in the target language in WebAssembly. So we try to make subtyping permissive enough that most of the time you can get away without doing something. So you have the usual width and depth subtyping on structs and arrays, but it's actually sound, so on mutable fields, it's invariant. So we just, only for that reason, we actually have to distinguish mutable and immutable fields, just to have more permissive subtyping while keeping soundness. And again, soundness is crucial, right? Because otherwise this whole strategy of no runtime checks would fail. On functions, you have the usual thing, contra-covariant subtyping, and that, means that in many cases, at least, source-level subsumption will just work when you after you've lowered your types. But of course, that doesn't always work, right? And it can't always work. It's basically impossible to have a type system in WebAssembly that can subsume all source-level type systems in the world, right? That will never fly, especially when you have this constraint that the Wasm type system should be simple and fast to validate, right? So we can't afford anything super complicated. So there are certainly limitations to that. Sometimes it won't work out and you need a workaround. So we need some kind of escape hatch. And the obvious escape hatch is casts. So the other thing we have as part of the GC proposal, it introduces the notion of runtime casts. So, for example, an instruction that's just a downcast and traps when it fails. So this is where the producing compiler knows by construction that it can't fail. It would use this instruction. But it can also use a branching cast where you can make a binary decision on a type. This is a type dispatch if you want. So this is really just an escape hatch for the low-level type system. It's not primarily intended to implement source-level casts, right? So you will also probably use it when you compile source-level casts, like casts in Java, instance of checks or something like that. But it may not be sufficient for that. For the same reason as before, we can never subsume all the source languages dynamic type systems either, right? So again, you need to do something in addition. And that is, in general, you have to implement your custom type representation if you have more complex runtime typing semantics in your source language. You have to implement that yourself, and at some point it will probably go down to WebAssembly casts, but that is just one part of the building blocks. Okay, so for the rest of my talk, I just want to run through a few examples of common things you implement for managed languages and how they would map to this thing. And basically, the whole idea is that none of that should be surprising. You basically should do the same that you do in the native code compiler, right? So this might just all be totally boring because I'm just showing you things you already know, but you just use them in WebAssembly as well. Before I do that, a very quick recap of some of the things about WebAssembly. For those who haven't seen it perhaps, so WebAssembly is a stack machine, so you have instructions like this. So this would be an addition of two constants, right? And that could be reduced to this one constant. And that's actually how the execution of WebAssembly is specified formally by a reduction semantic. So it literally says something like this as a reduction rule. Instructions are also typed, so that's what we get validation out. And since these are stack instructions, they all have a sort of function type, the left-hand side saying what you pop off the stack and the right-hand side saying what you push back to the stack. Like you see with the add instruction, it's like the obvious thing. And the main reason I'm showing you this is, so this is the WebAssembly text format, and one feature it has on top of this stack-like language is what we call the folded syntax. So you can actually write this sequence of instructions this way as well. So as if they were in expressions, right? This is really just syntactic sugar. It has no semantic meaning whatsoever. It's really desugared into the same thing, but it makes code much more readable because you see how things are grouped together. And that's why I'm showing that here, because I'm going to use that in some of my examples to make them a bit more readable. So when you see this, basically you can completely forget that there's a stack machine underneath. Just read it as a very verbose expression syntax, right? There's also structured control flow. I think I'm going to skip over that because it's not actually relevant to anything in my talk. So let's jump to examples. The most obvious one you want to see probably is how to compile classes, right? That's the ubiquitous thing in the object-oriented world. Let's take a simple example in some pseudocode language. I'm not picking any specific language here, but I guess this is something you can do write in a language like Java and others. So it's just a class with one instance variable, two methods. And let's say there's another class which is a subclass of that, which adds another method and another instance variable. And as most of you, I'm sure, know, is the standard way of compiling this is so an instance of C would be represented as a block of memory, which has all the instance fields. So A in this example, but the first thing is a method table pointer, or vtable as the C++ folks call it. So this vtable points to another heap or memory allocated data structure, which is just a vector of all the methods of that class. And this one is shared between all the instances of that class. And similarly for D, you just add the additional fields, but the structure is the same. So this is the kind of thing we actually need to lay out or emulate when we compile to WebAssembly as well, right? We have to implement that ourselves. At the same time, so D is supposed to be a subtype of C. So ideally, we want to define types in WebAssembly that preserve the subtyping relation, so that the layout for D, so a reference to D is actually a subtype for a reference to C. And that implies also that we have to have the corresponding subtyping between the method tables, so that the width subtyping works out. Okay, let's see how we do that. So first we want to lower the class C into type definitions. So we introduce one for instance, and that should just match exactly like this box I show you on the bottom. Unfortunately, my pointer isn't working here, so I can't really point at things, but you see what I mean, I hope. So it has this one instance field, which is the I64, and the first field is the method table pointer. And that again is just a struct of two reference to containing function pointers, which we also have to define as types. By the way, I'm using somewhat more pseudo syntax here for the type definitions. That is not really WebAssembly syntax, but that might be a bit more readable. I hope you appreciate that. So the function pointers we also have to declare as types, and you do it as you usually do when you compile these things. You have functions that take the appropriate arguments, but as a first argument, they always take a pointer to the instance itself, right? So this should all be very unsurprising. And similarly, we lower class C. Now the structs correspond to the boxes on the right, and they have these additional fields there. Otherwise, they are the same. And we have this one extra function, and that takes as a parameter a reference to a D, because it's a method introduced in class D. So far everything is great. This actually works out with respect to WebAssembly subtyping. The type D is a subtype of C, and so are the vtable types. All great. One more thing just for completeness. Let me also show how some of the code will translate. So say the function, the method f there, we lower that to a WebAssembly function on the bottom that takes the parameters as defined by the type there. So an instance pointer, the this pointer, and the actual parameter. And then we just do an addition on that, and the struct get there extracts the instance field from the instance, right? So this is just the struct get1 extracts the A field from type C. And for completeness, let's also look at an elimination side. So say we have some variable D, which is an object of type D, and we invoke the inherited method f on that. So that lowers into something like a call ref. So call ref is an instruction for calling a function reference, so an indirect call. And what reference are we calling? Well, the thing we have to call is the method f. So we have to, the only thing we have is a D, which is the instance. So we first have to get to the method table. That would be the struct get 0, the first struct get 0. And then we have the method table, and from that we have to extract the pointer to f itself, which is the second struct get. So this gives us a pointer to f. We call that, and in addition we have to pass the appropriate arguments, the first one being the this argument, which is D itself, and the constant, right? So again, I hope this is not surprising at all. I'm just showing you the obvious. So far so good. Now let's slightly modify the example such that D overrides F. This is where it gets a bit more interesting. So lowering of C doesn't change. For D, we now lower as before, except that here we now have in the method table for D, we have D.F. But one thing you see here is I wrote C there. Why did I do that? Well, and that is exactly where we run into one of the limitations of the WebAssembly type system, and this is obviously, of course, a well-known problem that the this argument is covariant in these objects encodings, but that doesn't work with contravariant sound function subtyping, right? So the WebAssembly type system isn't strong enough to know that the covariant subtyping would be sound here, so we can't use it. We actually have to use C there as well. So the type for DF has to be the same as for CF. Otherwise, the subtyping wouldn't work out on the WebAssembly level. If we do it that way, then it works out. But of course, that also has some implications for how we actually implement a method override. So just as a reminder, this is how CF looked, same as on the slide before. But for DF, the problem now is that we get as a parameter a reference to C, not D, right? So the first thing we have to do is we have to downcast it to an actual C, an actual D. And the producer, so the generating compiler, of course, knows by construction that this will always work out fine unless the compiler has a bug. But the engine, the WebAssembly engine, can't know that, right? It can't prove that. So that's why you have to do a cast there. Yeah, and then you do the addition as before. Okay, so this is one point where we run into limitations, and one of the things we maybe can lift to some extent in the future, but in general there will always be limitations like that. You will always have to use cast somewhere. So a related example is closures. I actually might want to skip over that because it's very similar. So this would be in a functional language where you implement closures, but if you know that closures are really, you can view closures as a degenerate case of a class that has just a single method, right? Which means that you can flatten the vtable into the object itself. That's how they are compiled. That's also how Java, for example, models closures within our classes. So the point being that you run into exactly the same problem here. So you define a specific closure type that is a subtype of the general closure type for a given function, and you have to do at the call side the same kind of downcast of the closure environment to the function's own environment type. And the same type system extension that would fix the thing for classes would also fix this thing for closures. So that's something I eventually want to get here. Another example, what do you do with generics? Well, we don't have generics in the language, so you do the obvious thing, you do erasure, right? So as a stupid simple example, let's say we have a generic pair of two-dimensional vector, if you want, over T, and we define two generic functions to just do the projections. Boring example, but fits on the slide. So because you can't do generics, well, you have to use the top type. The top type in WebAssembly is called any, so this is an any ref. I just declare the pair as a struct of two any refs. And then the functions, they just work out because they also just return any refs. There's nothing I have to do here, but I have to do something when I want to invoke these, right? So let's say I want to interpret this as a two-dimensional vector and want to compute its absolute value. So I have something like this function, which takes the square root of, oh, there are some invocations of square missing there, I just noted. Right, so there should be, both components should be squared, of course, for this formula to be correct. But despite my bad math here, this would be lowered somehow into WebAssembly, and my animation was somehow broken as well. So first of all, one thing we have to do is we have to define a type for boxed floats, right? Because we need something we can pass to this pair function that has to be a reference, so we have to box up floats. So that would just be a singleton structure that contains an F64. And then the function apps itself, well, what does it do? What you would expect, it has the two calls, and because they return any ref, it now has to downcast to the float type, the box float type, before it can access them. So that is another place where we have to insert casts, but this is really like how Java also does it officially, right? Okay, so let's switch again to the functional world a little bit and talk about algebraic data types or variant types. As an example for that, let's assume we are in a nice functional language and want to write an interpreter for WebAssembly itself. So we need to define some data type that represents the WebAssembly instruction set, right? So just showing a bunch here like knob and drop instructions and branches and blocks. So we need to lower this as well, of course. And the idea here is we want to do what functional compilers also do, which is unbox the nullary constructors. You don't want to heap allocate them because you really just want to represent them as an integer. They're really just like an index representing the constructor. So the type itself we want to represent as type any, which is kind of the union of all reference types. And then there are two concrete cases. One is I31, which is the unboxed nullary constructor case. And then the box case is going to be a supertype of all concrete constructors that are not nullary. So concretely, we have one type for each of the constructors that has parameters, which is a struct of the respective thing. But the first element of this struct is an index telling you what case you're in. And if you just have the supertype, you can use that to do your dispatch. So let's look at an example of how you would use this in practice or compile this in practice. So let's say we want to write an evaluator for WebAssembly. So part of that might be a stepping function, which takes a stack and a single instruction and returns the modified stack and possibly some kind of list of continuation instructions. And the way to implement that in a functional language is through pattern matching, obviously. Ignore all the right-hand sides, they don't really matter here, but what matters is that we do this pattern matching on the left, right? So we dispatch on the constructor of the data type. So how do we lower this? Well, we have a function that takes the respective parameters, so a stack and an instruction reference, and now we have to implement this dispatch. So the first thing we do is we look which case we are in. Is it a nullary constructor or not? So we do a branch on cast with the box type. We could also do it the other way around, but here I use the box type. And this cast, if it succeeds, this instruction would branch to some label L, which would be lower down in the function. I'm not showing that yet. And if the cast fails, it will just fall through, and the next instruction is executed. So in that case, we actually know, again, the producer knows by construction it has to be an I31 then, so it can just unconditionally cast that down to I31, the instruction, and then it can get the index out of that, so that would tell us what constructor we have, and then we do a BR table, which is dispatching on that number and jumping to some labels, one for each of the instructions we need to implement, and they would be somewhere further down in this function. And the other case is if we took the branch to L, so if we are in the non-nullary case, then we somehow get here, and there we can. One thing, it's a bit difficult to see here, but one thing that the branch instruction does is that the label actually receives the reference on the stack as well, but with a refined type. So when we arrive at L, we have on the top of our operand stack actually a reference not to the instruction type, but to the instruction N type. So we already know it's one of these things. So we can just get the index field there, And here's where the kind of function expression notation breaks down a little bit, because the operand to the struct get is already on the stack implicitly. We can't really write it here, but just assume that it's coming from the jump. So again, we just do a dispatch, a table jump on that index, and then the rest of the function just implements all these cases we have to jump to, right? That's all you do. Okay. And my final example is something called uniform representation. So that appears when you have a language that is highly polymorphic. So functional languages would be an obvious example where you have type inference and many types you infer are polymorphic actually, and you want it that way. The extreme example of that is, if you want, is actually untyped languages or dynamic languages where everything is polymorphic basically, right? And the thing is with these languages, so people who have not seen implementations of functional languages often assume when you have polymorphisms with generics, right? You can always just statically type specialize them. But that doesn't work in these languages because their type system is actually much too powerful for that. So they have things like first-class polymorphism, polymorphic recursion, other things that make it impossible to statically know all the instantiations that occur during execution of a program. This is related to what you also have in OO languages if you have virtual methods, as they would call them in C++. So generic methods, right? In C++, they are not allowed, and the reason is exactly that. It doesn't work with static type specialization. So for functional languages, this is like not an option at all because polymorphism is everywhere and it's typically first class and other features. So you can't do that. So, but also polymorphism is everywhere, so you're crossing the boundaries between monomorphic and polymorphic code all the time, and you don't want to do boxing, unboxing translation, conversions all the time either, because that would be very costly as well. So what typically these implementations do then is that they represent all values uniformly, so that you don't have to convert them. You all represent them as references in WebAssembly speak, under the type any, right? And then only when you need to access a value concretely, you have some elimination form, then you can't like cast it down or extract the correct type. So I implemented a whole like ML compiler on top of that as kind of a proof of concept thing. And I'm going to show you what kind of representation that used. But this roughly is what also the OCaml compilers would be using, or the Scheme compiler is using something very similar. So for example, the ML type has a type bool, which in this uniform representation you just represent as a I31 reference. There might be places where you can unbox it locally when you use an I8 or something, but in the general place you will always represent as an I31. And similar with characters, which are a bit larger than a bool, but still fit in an I31, so you can use that for that. Actual integer types, well, that might depend on what value range you want to have. So you could either use I31 as well, or you have to box it up into a struct, maybe even a struct with an I64 in it. You can also have a mixed representation, right, which would be, for example, what Scheme would be doing with its numeric tower, where you allow both these things and then convert as necessary. Floats you have to box up because they can't be stuffed into a reference. And then strings, well, just an array, like say an UTF-8 encoded array of bytes. Tuples, you already saw that with the pair example. That would be a struct of any refs now, right? Because the thing being with polymorphism, you can abstract the component types after the fact, so, and you never know beforehand when you have a tuple what context you're passing it into. So you can't assume beforehand that it will not be polymorphic some way. So you also have to use a uniform representation there. And I already showed you how well, I skipped over that, but I sketched how closures work. And data types I showed you on the last slide. ML also has a very advanced module system, which is higher order and everything, so that also would lower to structs and functions. But the point being here that, yeah, I31 is relatively important here so that you can have all these unboxed representations. Okay, those were all the examples I wanted to show, just like as my last slide, essentially, a number of limitations. So the one you already saw, of course, is that we have to do casts in a number of times. And some preliminary numbers reported by us, by the compiler writers, was that they saw like 2 to 4% overhead in that. So V8 has an option to turn off the runtime checks for casts. So you can measure that quite easily, what the cost of the actual casts is. I also said that there's no automatic interop between languages, so you need to define your own APIs. And then maybe more interesting thing is that, well, this is of course a feature that has to cover certain use cases, but there will always be use cases that can't cover. So there are languages that have very particular needs for their GC. So one example would be Go, which made this interesting design choice to allow interior pointers into objects, which we can't directly represent because we don't want to burden every WebAssembly engine with implementing this mechanism because it's quite horrible. Then there are languages like Prolog or Haskell, which have things like logic variables or lazy thungs, which once they get bound can produce chains of indirections that usually their garbage collectors want to shorten and eliminate. Maybe there's a way to get an abstraction for that, but right now they wouldn't be able to use this optimization. And the biggest one is where we're still kind of like have no good ideas what to do about weak reference finalization, right? There are so many different semantics for that out there. Every language has its own. They all are incompatible with each other. Some even have 3 different versions of it. So what is the right abstraction for this kind of thing? That doesn't mean that we're adding all of them. And also what does maintain all the good properties we want to have. And a final thing I need to mention is one of the drawbacks of having this typed assembly language is, of course, that a compiler targeting this language has to produce this type information. And that could be problematic if you have a legacy compiler which throws away its type information too early in some of the representations. Then it might not have enough information in the backend to generate this, right? So if you have a compiler and you want to write a new backend that targets the Wasm GC extension, then this might be a problem for you and you might have to do some extra work. Okay, that's basically what I had. Yeah, the main takeaway I wanted to bring across is that this is, although it's GC, it's low-level GC, and you still have to do everything you have to do on native, more or less, minus implementing the actual GC. That's the only thing this extension gives you. And this is like a version 1.0 feature, so there definitely is much room for improvement, and we will, based on feedback on what we get from clients, I'm sure we will add more stuff to that over time. Okay, that's all I had. Just a reminder, and I'm happy to take questions.
We have time for a couple of quick questions. Anyone wants to come to the mic?
So I imagine that there will be some runtimes that choose not to implement the GC proposal for one reason or another. One, I guess, is that permitted? And even if it's not permitted, they're going to do it anyway. So what effect do we think that would have on the ecosystem? Would it bifurcate the ecosystem into Wasm modules that run on those runtimes and
Right.
Wasm modules that do not?
Yeah, that's an excellent question, and there's an ongoing discussion about that, introducing some notion of profiles into WebAssembly. I think this is absolutely essential. GC is not the only feature that some ecosystems might not be able to implement, like threads is another, continuations is another, SIMD is something that is super large and like an embedded platform might not care about or not get any benefit out. So what I have proposed is that we introduce like a general framework for defining profiles, which define very precisely certain language subsets. And then these environments can pick whatever subset they can handle, right? And GC should definitely be like a profile or GC-less. Determinism is another important one, by the way. For blockchains, they absolutely need a deterministic semantic, so there's going to be a profile for that.
You didn't actually talk about GC itself.
Right.
I'm curious, one thing is, does it have to use the static type information?
What?
The sort of static type information, does it need like metadata associated with variables and so on
So-
to trace the references?
Of course, the specification doesn't say anything about the GC, right? You just just works. But there are some implicit assumptions, of course, about the performance of a GC. Like, since you can do rather fine-grained allocations, a GC should be able to handle frequent and fine-grained allocations. Other than that, it's completely up to the engine and probably the environment it's running in, right, which is the best implementation technique for that. We don't prescribe anything in particular. That's left for quality of implementation issue and depending on ecosystem, hardware, whatever, right?
Other than it has to be type safe.
Yeah, but that is validation, right? Like that is not, the GC itself doesn't, I mean, operationally, this whole feature is actually quite straightforward. There isn't anything fancy happening here. It's all that we have to validate it so that we know that nothing bad can happen when you access GC objects.
I guess I'm missing something then, because I mean, I'm familiar with the C#, the .NET GC, and it actually has to look at type information so it knows object layout and so on. But you've got
Right.
that implicitly in the objects.
Yeah, you need to have some minimal type information, of course, so you need to be able to distinguish these four kind of reference I showed you, right? But that is much simpler type information than the actual WebAssembly type system, right?
Okay, thank you very much. Let's switch to the next speaker.
Yeah.